Good day everyone and welcome to another video. In this lecture, we will be dwelling deeper into the concepts and calculations on momentum transfer as well as some insights on viscous flow. So let's get started. Let's define the forces acting upon fluids when they flow. We have two basic types of forces which are differentiated by the direction of action. We have normal force that is directed perpendicular to the area acted upon, while shear force is directed parallel to the area of action. For our discussion of momentum transfer, we will be focusing on the shear stress as it is the main parameter assessed in moving fluids. We define shear stress as the ratio of shear force and area of action. And we can also refer to it as the momentum flux as we had done in the previous videos. Building upon our previous discussion, we will now be interpreting Newton's law of viscosity. Remember that this law applies to the molecular transport of momentum in a fluid system. We call the slow and orderly flow of a fluid as laminar flow. One of the defining features of laminar flow is the existence of distinct fluid layers, and these layers remain separate and have differing velocities. The difference in velocities of the fluid layers is what causes momentum transport. Let me visualize the velocity profile for you using a deck of cards. So I have here a regular deck of cards wherein each card acts as a fluid element. So you have many infinitesimally thin fluid elements stacked together to form your fluid. Take a look at what happens to the fluid when a shearing stress is applied at the top. What happens is that the fluid layers do not move all at the same time. The fluid layers at the top are the very first one to move, and we interpret that as them having the highest velocity in the system. While the bottommost cards, the card that is in contact with my hand, which is a solid boundary, is not moving at all. That is a very important concept called the no-slip boundary condition. Shown here in the figures in the presentation are what we call velocity profiles. The velocity profile of a system lets us determine the velocity of a fluid layer at any given position. If you take a look at these figures, we have a plot of the velocity as a function of position. At different points of y, you have differing values of velocity. The longer arrows denote higher velocities. And at the point wherein the fluid is in contact with the boundary, the velocity is 0 because of the no-slip boundary condition. Effectively, this means that the bottommost fluid layer is stuck to the fluid surface. So if the fluid surface is stationary, then the bottommost layer of fluid is also stationary. But if it starts moving, then the fluid layer also starts moving at the same velocity as the boundary. Notice that as we go farther and farther to the boundary, the velocity increases. So this is a defining characteristic of the flow of a fluid past a solid surface. As you go away from the boundary, your velocity starts to increase until it reaches a maximum value, which is at the free surface of the fluid, meaning it's no longer influenced by any solid boundary. Next, let's examine the figure on your right. This is the same boundary profile, however, your system here is now changed. It is now a fluid flowing on the space between two plates. So we now have two boundaries, the one at the top and the one at the bottom. As you can see on the velocity profile, we have 2 points here wherein the velocities are 0. The topmost and the bottommost because they are the ones in contact with the solid surface. That's again because of the no-slip boundary condition. Now with this figure, let's determine where is the point at which the maximum velocity exists. So in this case, the maximum velocity is expected to exist at the point that is farthest from any boundary. On the previous example, the point farthest from the boundary is the free surface. That's why this is the point of maximum velocity. However, in our second example, we have two boundaries at the top and at the bottom. So the point of the fluid that is farthest away from the boundary is at the middle. So this is where the maximum velocity occurs, as you can see on the representations of the arrows. It is also at this point wherein the shear stress is at the minimum. So the maximum velocity corresponds to the minimum shear stress, while the minimum velocity corresponds to the maximum shear stress. This is a velocity profile, while this is a shear stress profile. This is a stationary picture of the case for laminar flow. you see here that we still have two boundaries. The boundary at the top is moving because of the force exerted, and the boundary at the bottom is stationary. The velocity is 0. As the top plate moves, the fluid layer that is directly adjacent to the top layer is also moving at the same velocity as the plates. The same can be said true for the fluid element at the bottommost, which is adjacent to the bottom plate, which are both not moving. And those are consequences of the no-slip boundary condition. This is a moving animation of the phenomena. Now, in order to fully appreciate this, you need to focus your sights at the bottommost layer. So see that the bottommost layer is not moving, while each progressive layer starts to move faster and faster until you reach the maximum velocity at the free surface. Do not forget the terms free surface. This refers to the surface of the fluid which is unhindered by any boundary. The solid boundary is a junction wherein a fluid touches another object. Okay? And at the solid boundary, we can use the no-slip boundary condition. With that, let's try to solve a problem regarding Newton's law of viscosity. Refer to the figure below. If the top plate is kept still, and the lower plate is moving at a rate of 10 centimeters per second, and the fluid flowing between the plate is ethanol at 273 Kelvin, calculate the shear stress and shear rates encountered by the fluid. The thickness of the film is 0.5 centimeters. So let me first draw the given. Okay, we have here our given. So this is a classic example of a fluid flowing between two plates, wherein one plate is kept stationary and the other plate is moving. So expect to encounter more problems like this regarding momentum transport. Okay, so our main equation here is Newton's law of viscosity. That is, tau is equal to negative mu, that's du over dy. Now, let me just clarify some of the important subscripts that you need to place on your variables. For the velocity, which we represent with the letter u instead of the letter v, to disambiguate from the letter nu, which we are using for momentum diffusivity, you need to place a subscript for the velocity that denotes where is the direction of the flow. So from our example, the flow is from left to right, and that is through the x-axis. Therefore, we say that this is the velocity along the x-axis. Okay, what about your shear stress, tau? What should be the subscript of tau? So normally, we are placing two letters as a subscript for tau. The first subscript is to what direction is the shear stress varying? And the second subscript is to what direction is the shear force acting? Okay, so the first one is to what direction is it varying? The second is to what direction is it acting? So based on our example, the shear stress is varying along the vertical direction because the fluid layers are separated in the vertical direction. So our first subscript should be y. The second subscript is to what direction is the shear stress acting, and that is on the horizontal direction x. Therefore, our subscript for tau is yx. We read this as the shear stress acting on the x-axis varying on the y-axis. Okay? Do not interchange these two subscripts. Okay, so with this working equation, what we need to do is we need to integrate this equation, and we are going to assume here that the shear stress is constant so that we can easily integrate this differential equation. However, we first need to determine the viscosity of ethanol at 273 Kelvin. This is the reason why I asked you to practice obtaining the transport properties of substances, because we will be doing this a lot in our calculations. And for that, we need to take a look at our handbook. If you are using the 8th edition of the Paris Chemical Engineer's Handbook, the viscosities of inorganic and organic liquids are given here in table 2-313. So we simply look for ethanol, and then we get its constants from C1 to C5. So ethanol, okay, here's ethanol. C1 is 7.875. C2 is 781.98. C3 is negative 3.0418. And then there's no C4 and C5. So we can say that C4 and C5 are both 0. So this simplifies our equation. Our equation for the viscosity is given at the bottom of this table. So this is it. For liquid viscosity, the equation is mu is equal to exponential of C1 plus C2 over T plus C3 ln of T. And we stop there because C4 and C5 for ethanol is 0. Okay, going back. So we simply have to substitute our constants and our temperature in order for us to find the viscosity of ethanol. So that is E raised to C1 7.875 plus C2 over T 781.98 over 273 Kelvin plus C3 ln of T, but C3 is negative, so that's minus 3.0418 times the natural logarithm of the temperature, 273 Kelvin. Our viscosity for ethanol is 1.794 times 10 to the negative 3 Pascal seconds. Now that we have the value for the viscosity of ethanol, we can now go back to Newton's law of viscosity in order for us to determine the shear stress and the shear strain. So by the way, the shear stress is our tau, and the shear strain is our gradient dux over dy. So let's first solve for the shear stress tau. By the separation of variables, we now have tau yx multiplied by dy is equal to negative mu multiplied by dux. Now let's integrate. For our limits of integration in the left-hand side, we will integrate from y1 is equal to 0 up to y2 is equal to 0.5 cm. If we convert that to meters, that is 0.005 meters. We want to convert that to meters because our final answer would then be in SI units. Now, why are my limits for y 0 and 0.005? That's because the thickness of your fluid elements is 0.5 centimeters. So we are simply taking its y position at the bottom and the y position at the top as the limits of our integration. Next, what about our limits of integration for the velocity? We have two values of velocity, and since the bottom plate is moving, the fluid velocity at the bottom would be expected to be the same as the velocity of the moving plate, and that is 10 centimeters per second. If we convert that to meters per second, that is 0.1 meters per second. So our limits of integration would be from u1 of 0.1 meters per second up to a u2 of 0. Okay? And postulating that shear stress, tau, and the viscosity mu are both constant, we can remove them from the integral and simply evaluate the integral of dy and the integral of du. So we now have tau yx multiplied by y, limits of integration from 0 to 0.005 is equal to negative mu times ux, limits of integration from 0.1 to 0. Substituting the limits of integration and rearranging the equation, we now have tau yx is equal to negative mu multiplied by, for u sub x, that is 0 minus 0.1 over for y, that is 0.005 minus 0. At this point, you simply substitute the viscosity of ethanol. That is already in Pascal seconds, and those are standard SI units. So our result for this calculation for the shear stress would have a unit of pressure, that is pascals. Let's calculate. That would be negative 1.794 times 10 to the negative 3 times the ratio 0 minus 0.1 over 0.005 minus 0. So this is our shear stress, 0.036 pascals. Okay? That is how we manipulate the Newton's law of viscosity. For the next question, we are asked to solve for the shear strain. The shear strain is simply the gradient in Newton's law of viscosity, that is du over dy, or in simple terms, that is delta u over delta y. So let's solve for the shear strain. So for the shear strain, we have du x over dy, which is numerically equal to delta ux over delta y, and that is the same as this in our Newton's law of viscosity. This is 0 minus 0.1 over 0.005 minus 0. If you're wondering about the units of this shear strain, let's take a look at the units of the numerator and the denominator. Your numerator is a difference in velocity, so that is meters per second. And your denominator is a difference in position, and that is meters. Okay? Rearranging, your unit for shear strain is per second, or 1 over second. And solving for the numerical part, we get that's 0 minus 0.1 over 0.005. The answer is negative 20 per second. This is our shear strain. Normally, shear strain is represented by the letter gamma. Okay? If you want to check, you can multiply the shear strain with the viscosity and you should arrive with the shear stress. So let's multiply negative 20 with negative 1.794 times 10 to the negative 3. We get the answer for the shear stress, 0.036 pascals. Okay? So this is how we solve such types of problems. Okay, let's proceed. Now let's transition to the different types of fluids and how do they behave under stress. Up to this point, we have been talking about Newtonian fluids as having constant viscosity. That's because the graph of the shear stress versus the rate of shear strain for Newtonian fluids is a straight line, meaning the slope, the viscosity, is constant. But there are other types of fluids besides Newtonian fluids. In fact, in many industrial applications, some of the fluids being used there are not Newtonian at all. So we have here some different types of non-Newtonian fluids, and we will be discussing dilatant and pseudoplastic. Let's start with dilatant. An example of a viscosity changing fluid are dilatant fluids. We also call them shear thickening fluids because when you apply a force into them, their viscosity increases. You see that the slope of the curve for dilatant fluids increases as the shear strain increases. As you exert more force or shear stress, then the viscosity increases. That makes it harder for the fluid to flow under stress. A classic example of a dilatant fluid is the cornstarch and water mixture. At a certain proportion of ingredients, this mixture resists flow and deformation if you exert a force, such as punching or slapping. But the moment when you stop applying the force, the viscosity decreases and it flows easily. The opposite of dilatant fluids are called pseudoplastic or shear thinning fluids. So this is the graph for pseudoplastic fluids. You can see that as you increase the rate of shear strain, the slope of this curve gradually decreases, meaning that the viscosity of the fluid decreases. So viscosity decreases as force is applied to the fluid. Common examples of pseudoplastics are ketchup and paint. You oftentimes need to exert some force into a ketchup bottle in order for its contents to flow. And some types of paint needs to be stirred first before application to reduce its viscosity and to avoid a very thick application of paint. We also have other types of fluids such as Bingham plastics, which are pictured here. They need a certain amount of yield stress, or you should be first meeting a threshold amount of stress before they can start flowing. I just want you to be familiar about Newtonian, pseudoplastic, and dilatant fluids. Next, let's characterize viscous fluid flow. This characterization of viscous fluid flow brings us back to the concept of laminar flow. So how do we determine if the flow is laminar or turbulent? Of course, we are curious because laminar flow is molecular transport, meaning it's an orderly transport, while turbulent flow is turbulent transport, which is chaotic. In order for us to determine that, we turn to the classic Reynolds experiments. In this experiment, there is a clear tube in which water is flowing at a steady, controllable rate. Therefore, it has an adjustable velocity. A small amount of dye is steadily introduced at the center of the tube to help us visualize the flow. Because water is transparent, we need to incorporate a colored dye in order for us to see what's happening inside. If you notice a straight line flow of the dye, meaning that the dye travels at a straight line at the center of the pipe, that is indicative of laminar flow. That's because there's very little mixing between the fluid layers and the dye is not scattered within the matrix of the water during the flow. So as you increase the velocity of the water, or as you increase the flow rate of the water in the tube, the dye stream starts to become erratic, or it starts to become chaotic. The dye starts mixing with the entire tube of water, and that is what we call turbulent flow. Turbulent flow is generally encountered as we continue to increase the velocity of the fluid flowing inside the pipe. We can classify fluid flow as either laminar, turbulence, or in transition between laminar and turbulence based on the value of the Reynolds number. We mathematically define Reynolds number as the ratio of inertial forces to the viscous forces within the fluid flowing. For our applications, we will be using this given formula of Reynolds number. This is L U rho over mu. L is the characteristic length of the conduit. If the conduit is a pipe, L becomes the diameter of the pipe. If it's a flat plate, then it's the entire length of the flat plate. U is the velocity of the fluid. This is average velocity. Rho is the density of the fluid, and mu is the viscosity of the fluid. Two of these properties, density and viscosity, are dependent on the physical properties of the fluid, while the other two, characteristic length and velocity, are dependent on the conditions of flow of the fluid. So when you calculate the value of the Reynolds number, if we get a value of 2,100 and below, that is considered as laminar flow if the fluid is flowing inside a pipe. For Reynolds number greater than 4,000, that is characterized as turbulent flow. And for the values between 2,100 and 4,000, we call that the transition region. The transition region is a mixture of laminar and turbulent flow. So it's not fully laminar, it's not fully turbulent, it's under transition. It is in the transition region where we start to see the formation of eddies or little swirls that signal the transition from laminar to turbulent flow. Let's solve the first example. We have water at 30 degrees Celsius flowing at a rate of 10 gallons per minute inside the tube with internal diameter of 2.067 inches. Determine the Reynolds number of the fluid. So let me first list the given. We're given our fluid, which is water, at 30 degrees Celsius. The volumetric flow rate Q is 10 gallons per minute. The diameter of the pipe is 2.067 inches, and we are to determine the Reynolds number. Okay, let's first start with the determination of the properties of water, because if you will remember, Reynolds number is characterized as d u rho over mu for fluid flow inside pipes. So let's first determine the density and viscosity of water. Converting 30 degrees Celsius to Kelvin, we have 303 Kelvin. You can also use 303.15 Kelvin, but that would entail more calculations for interpolation. For the density of water, we can find that in our handbook under chapter 2, density of saturated liquid water, that is table 2-30. Our temperature, 303 Kelvin. That's between 302 and 304, meaning we just have to get the average of the two density values. We get the average between 995.948 and 995.346. Our density is 995.647. Units, kilograms per cubic meters. Next parameter, Viscosity. I have already showed you where to find the viscosity of substances. It is in table 2-313 under transport properties. Okay, so this is our equation. These are our constants for water. For C1, that is negative 52.843 plus C2 over T 3703.6 divided by 303 Kelvin plus C3 5.866 times the natural logarithm of the temperature 303 Kelvin plus C4, that's negative 5.879 times 10 to the negative 29 times temperature 303 raised to C5 10. This is the viscosity of water at 30 degrees Celsius, 8.22 times 10 raised to negative 4 Pascal seconds. Please practice obtaining physical properties of substances. Before we substitute everything to the Reynolds number, it's better if we start converting some of the values to SI units. The diameter, which is given in inches, can be converted to meters by multiplying with the ratio 1 inch is to 0.0254 meters. 2.067 times 0.0254, 0.0525 meters. Now, we are given the volumetric flow rate of the fluid, but what we need for the Reynolds number is the velocity of the fluid. We can use the definition of volumetric flow rate. That's Q is equal to U times A, wherein A is the cross-sectional area of the pipe. So that is U times pi over 4 d squared. Solving for the velocity, we have volumetric flow rates over cross-sectional area, pi over 4 d squared. So our internal diameter is already in meters. With that, we have to convert our volumetric flow rate to cubic meters per second in order for us to have homogeneous units. So our 10 gallons per minute, we use the factor 1 gallon is 231 cubic inches. And then 1 inch is 0.0254 meters. The factor is cubed. For the last factor, we have to convert minutes to seconds. So 1 minute is to 60 seconds. For the denominator, we have pi over 4 times 0.0525 meter quantity squared. And with that, we can solve for the average fluid velocity. That is 10 times 231 times 0.0254 cubed divided by 60. All over pi over 4 times 0.0525 squared. Our fluid velocity is 0.29 meters per second. Now we are ready to substitute everything to the Reynolds number. So diameter, velocity, times density, 995.647 kilogram per cubic meter, divided by the viscosity of water, 8.22 times 10 to the negative 4 Pascal seconds. Solving, that is 0.0525 times 0.29 times 995.647 divided by 8.22 times 10 to the negative 4. So we have a Reynolds number of 18,441. And since this Reynolds number is beyond 4,000, we say that the flow is turbulent. Okay, so that is how we classify the regimes of flow through the Reynolds number. Okay, let's go back. Okay, number 2. Whole milk at 293 Kelvin, having a density of 1030 kilograms per cubic meter and a viscosity of 2.12 centipois, is flowing at a rate of 0.605 kilograms per second in a glass pipe having a diameter of 63.5 millimeters. Letter A, calculate the Reynolds number. What type of flow is described? So this is just the same as our previous example. And letter B, calculate the maximum flow rate possible for the flow to be laminar. Also determine the average velocity of the fluid. I will be leaving you this problem for you to practice your calculations, okay? But I will be giving the layout of the solution so that you will have a guide. Here are the given. So you are given the density, viscosity, mass flow rate, and diameter. For letter A, you are to compute for the Reynolds number, du rho over mu. So we were already given the viscosity, the density, and the diameter of the conduit. What you do need to solve for is the velocity of the fluid. And you can get the velocity of the fluid from the mass flow rates. The mass flow rate is defined as density multiplied by velocity multiplied by the cross-sectional area. So we can also write this as rho u times pi over 4 d squared, such that when we solve for the velocity, it's simply the mass flow rate over the density times pi over 4 d squared. Okay? And then you can substitute these values to the equation. However, you need to convert the diameter to meters, and you need to convert the viscosity from centipois to millipascal second. Our conversion factor is 1 centipois is equal to 1 millipascal second. So therefore, 1 centipois is equal to 1 times 10 to the negative 3 Pascal second. Okay? So you can substitute these values and you can solve for the value of the Reynolds number and discern what type of flow is present. For letter B, calculate the maximum flow rate possible for the flow to be laminar. Also determine the average velocity of the fluid. So for you to be able to keep the flow laminar, you have to keep the Reynolds number at 2100 because this is the maximum value of Reynolds number that will still allow laminar flow. So given the value of the Reynolds number, you can substitute it in this equation and back substitute for the value of the velocity. This velocity is called the maximum laminar velocity. It's the maximum allowable velocity of the fluid at these conditions in order for the flow to still remain laminar. So you can solve for that. For the follow-up question, determine the average velocity of the fluid. You can skip this first because we will be discussing the difference between average and maximum velocity in a future lesson. Okay, so skip this question first. You stick with the Reynolds number first. So that is your practice problem. Okay, we now know that turbulent flow happens at Reynolds number beyond 4000, meaning that is for fast flows. Since we have now introduced the concept of turbulence, let's try to understand more about its concept because it's a very complex phenomena. A simple way of describing turbulence is that it is chaotic, random, and highly disordered. For those of you who have ridden an airplane before and have experienced turbulence, the shaking is caused by a lot of factors including disruptive air streams and rising hot air that disturbs the laminar flow of air around the wings and body of the airplane. So basically, it's turbulence in a larger scale. The same is true for any fluid flowing for high velocities. Shown here is the transition from laminar flow to turbulent flow. You see that there is still orderly flow in the laminar region, but as you then continue to increase the velocity, we enter the transition region. In the transition region, we still retain some of the characteristics of laminar flow in which there is still some degree of orderly flow, but eddy currents or eddies start to develop. Eddies are also called vortices or swirls. So you see here are the swirls. As the velocity continues to increase, the transition fades and the flow becomes highly chaotic and highly turbulent. For a fluid flowing past a surface, such as what is demonstrated here, the flow is not entirely turbulent even if we drastically increase the fluid velocity. You will still find a thin layer of fluid called the viscous sublayer that retains the laminar flow. This is again due to the no-slip boundary condition. As you increase the flow velocity, the viscous sublayer becomes smaller and smaller, and the velocity gradient that we commonly see for laminar flow becomes flat and more homogeneous, as you can see here. The flattening of the velocity profile over the turbulent region here means that the fluid velocity is now more evenly distributed across the matrix of the fluid. But it would still retain some of the laminar flow in the viscous sublayer on which the no-slip boundary condition still acts, and the velocity of the fluid adjacent to the boundary is still 0. So we still have a buffer layer and a viscous sublayer that displays up to some degree laminar flow. Since turbulent flow is highly chaotic, it becomes very hard for us to analytically describe its behavior. For a fluid under turbulent flow, small parts of the fluid could exhibit different velocities, although this becomes averaged out when we compute for the fluid velocity. So there are local variations within the velocity of a turbulence flow. This localized variation is difficult to describe exactly. That's why equations describing turbulent flow rely on statistics and experimental results to determine its averaged behavior. What we are actually solving is just the average behavior derived from statistics. Shown in this figure are the velocity profiles for laminar and turbulent flow for flow inside a pipe. The laminar flow is more parabolic and the turbulent flow is more flat at the top. The velocity profiles vary in their shape mainly because of the distribution of velocities along the dimension of the pipe. This is in accordance to what we have discussed earlier. Even though the flow inside the pipe is turbulent, we are still retaining some of the laminar flow in the viscous sublayer. The velocity profile of the turbulent flow features a wider parabola at its peak, as the highest fluid velocities are now found within a larger central area of the pipe compared to laminar flow, because laminar flow is much more affected by the no-slip boundary condition than turbulent flow. We will be deriving the velocity profile for laminar flow in different conduits in our next lesson. To close this lesson, I would like to leave you with some problems that you can practice solving on your own. The solutions to these problems are found in a separate video which I will be releasing later. Try solving these problems first before watching the solutions video so that you can develop as a learner. And with that, that's it for this lesson. I hope you have learned something. See you in the next lesson, and as always, keep safe.